This is a video introduction to the idea of titrating weak acids with strong bases, or weak bases with strong acids. Material from Chapter 10 of your textbook. So, when we talk about a weak acid strong base titration, we can talk about it in terms of the four traditional regions that we've been talking about for titration curves. First one being before we add any titrant, just a point, not really a region. Second one being between the start of the titration and the equivalence point. Third region being at the equivalence point, and then the fourth excess titrant being present. So let's walk through a problem. Imagine that we titrate 25 milliliters of a 0.1 molar weak acid, uric acid, with 0.2 molar sodium hydroxide, a strong base. In the first region, the pH is just dictated by the weak acid that's in solution. So we have a 0.1 molar solution of weak acid. To find its pH, we need to consider the equilibrium and the extent to which it dissociates, which is given by the Ka. So we can make a nice table if we want. Figure out that the total proton concentration basically all comes from the uric acid, and use the Ka, solve for x. And when we solve for x in this case, we get a number. We take the negative log of that number, because x is the hydrogen ion concentration, and we get a pH of 3.3. Very straightforward, simple equilibrium problem when we haven't added any titrant yet. So to make our titration curve, we just put a point there. pH 3.3, no titrant added. As we begin to add titrant, we need to ask ourselves a few questions. First one being, how much weak acid did we start with? Well, that's given in the problem. 2.5 times 10 to the minus 3 moles. How much strong base did we add? Also now given by the problem, dictated by the amount of titrant that we've added so far. And so we can figure out how much of the uric acid is left. Half of it's left, half of it was reacted with the hydroxide ion. When it reacts with the hydroxide ion, it forms its conjugate base, the urate ion. And so this point in the titration is equivalent to mixing 1.25 times 10 to the minus 3 moles of uric acid with that same amount of sodium urate. Now, this phrasing it this way should help you recognize that this is a buffer system. So we need to use the Henderson-Hasselbalch equation. When we do this, we can just put in the numbers on the previous slide. The pKa is just the negative log of the Ka. And the urate concentration and the uric acid concentration are equal. We know we had the same amount. You can divide by the volume and convert to molarity, but you don't really have to. In either case, this ratio of conjugate base to acid is going to be 1 at this point in the titration, and so the pH is going to equal the pKa for the weak acid. This is the midpoint of the titration. So our titration curve so far, we start out at pH 3.3 and we have a gradual rise up towards 5.6. Now if we go a little past the midpoint, we can do the same thinking as before to figure out how much uric acid is left. We still have a buffer because we still have a weak acid in solution with its conjugate base, but now this ratio in the log term is not exactly 1, it's a little different. And so the pH is going to equal 5.7 instead of 5.6. This is still in the buffering region, but it's not the midpoint. So we have another point that's just a little higher. At the equivalence point, our third region, we can think about this in the same way. If we don't know this is the equivalence point, we can think about the same things. How much weak acid did we start with? How much strong base did we add? We see they're equal. So, this is the equivalence point. All right. Now we have a couple of equilibria that are going to be involved. We have, first of all, this reaction, which is going to be reaching completion. Second of all, we have the water autoionization, which may be important or it may not. What we have to ask ourselves is, what's our urate concentration? And what's the Kb of that urate ion, the weak base? And so we can do a little math and solve for the hydroxide ion concentration, keeping in mind that a solution of water contributes 1 times 10 to the minus 7 molar hydroxide ion from water autoionization. In this case, not really significant. You get the same number for the pH either way. But if the hydroxide ion concentration was lower, we would want to take that into account. So at the equivalence point of this titration, our pH is going to be 9.21, higher than 7. Because this is a weak acid titration, not a strong acid titration. Our titration curve then looks like this, where we have a gradual rise almost all the way to the endpoint and then a steep rise at the endpoint, just like every other titration curve we've talked about. And then after the equivalence point, we have hydroxide in excess, so we do all the same stuff as before, figure out how much extra hydroxide ion we have left over, and that dictates our pH. So our pH after the endpoint is 12.1 units after we've added a few more milliliters. And so what we get is a titration curve that looks like this, where it is a steep rise out of the equivalence point, and then a slow, more gradual rise up to a pH that's over 12, where it will level off.